Our next chapter is chapter 7, which is all about water and solutions. So we're actually going to start by talking about solutions, some of the terms, some of the math, what happens if it's not a true solution, the particles are too big, and then we're going to get into some ideas with water, and is water pure or not? So solutions have some terminology that we have to become familiar with. The first is, what does a solution composed of? It's composed of at least two parts. We have the solvent and the solute. The solvent is the part in larger quantity. Now for us, that solvent is normally going to be just water. It could be other things. If you take organic, you can do hexane or benzene or something else. But for regular chemistry and regular life, water is the most common. Solute is the component in lesser quantity. So let's say you were going to make up some Kool-Aid. The part that's in biggest quantity, well, that's water. And then in that case, you actually add two different solutes. You add your Kool-Aid packet, and then you also add your sugar. So you have two solutes there. Now, that Kool-Aid is going to make what's called a homogeneous or homogeneous mixture. That just means that it has uniform composition. It looks the same top to bottom, and everything is in the same phase. Versus heterogeneous, where there's different phases that you might see. But it doesn't always have to be a liquid in a liquid. You can actually put any phase in a liquid in water and it will dissolve, it'll be fine. But you can also have some other phases. So aqueous or aqueous, however you want to say it, means dissolved in water. You can also have what's called an alloy. An alloy is a solid solution. So some examples, opals or actually no, we're not going to talk about opals yet. Sorry, that's a further thing down the line. Steel is an example. Steel is actually iron with just a little bit of carbon in it, up to about 2%. And gold. So you might think, wait a second, gold's on the periodic table. Well, gold a lot of times is used for jewelry. And if you get 24 karat gold, that is pure gold. That's the thing that comes on the periodic table. But that gold is super malleable. In fact, it's so malleable, it's actually not the most useful. They like to mix other metals in there to make it to where it'll hold its shape just a little bit better. It won't bend. So what they'll do is they'll add silver or copper or nickel to make it to where it's a little bit easier to work with. So if you get 18 karat gold, that's 75% gold. 14 karat gold is still 58% gold, but it's a solid in a solid. You can also have a mixture of gases that could be considered a solution. I mean, the air that you breathe is an example of that type of solution. So this slide, and this just came straight out of your book, this emphasizes the fact that solutions can be in any phase. They have the gaseous solution in the back, which is just the air that we breathe, which we learned before is mostly nitrogen with some oxygen and some other things. The liquid solution that they have is a little thing of champagne, so you have water and ethanol and some carbonation in there along with some flavorings. And then the solid solution, the gold ring right there, that's an alloy. That one talks about an 18 karat gold ring, which is 75% gold and 25% other metal. Now, you can't just add as much solute as you want to in a solution. There's actually a limit to the amount of solute that will dissolve. That's called solubility. So the measure of degree to which the solute dissolves in the solvent. Now, this is highly dependent, as we're going to learn, on temperature and also on the chemical nature of the substances that you have. But let's look at a couple of terms. The first term we want to look at is saturated. Saturated means it contains the maximum amount of solute. Now, we've heard about saturated before when we were talking about saturated fats and oils. And what that meant was that that molecule had as many hydrogen as it possibly could. And unsaturated means that it had some double bonds to where it could actually have more hydrogen. You could force more hydrogen onto that molecule. So let's talk about it in terms of solutions. So I'm going to give you an example. I'm going to use the example of sweet tea. I stopped drinking pop a few years ago. It's a very good decision on my part, but I do really still enjoy sweet tea. And it has to be like good sweet tea. So if I'm at a restaurant and I ask for sweet tea and they bring me a glass of iced tea in the sugar packets, I can't get it sweet enough for myself. But let's talk about what happens. So you rip open that first packet of sugar and you add it and you stir it up. It all dissolves. Now at that point, that solution is considered to be unsaturated. I could still add some more sugar to it. So I add another packet, dissolves, still unsaturated. I can add more. I get to that third packet of sugar. Okay, I kind of like sugar in my sweet tea. And I pour it in and I stir it and stir it and stir it, but it doesn't all go into solution. The excess just kind of drifts down to the bottom. Now at that point, that's considered to be saturated. It's holding just as much as it possibly can. Anything else that I add is just going to go to the bottom. But that was not sweet enough for my taste, for my sweet tea. So I like, or the way that you make a good sweet tea is you need to have what's called a supersaturated solution. What supersaturated means is that as you're making that solution, as you're making that tea, you heat it up. Because when you heat up most things, it'll hold more solid. Sugar does amazing at this. So as you're brewing the tea, that's when you start dumping in the sugar and you mix it all up while it's hot. And then you carefully cool it down. As you carefully cool it down, that solution does become somewhat unstable. Now with sweet tea, it's fine that the sugar stays in solution, but there are some other substances where they have a tendency to come out of solution, such as sodium acetate's one that does that a lot. Now over on the right hand side, I have a picture of a supersaturated sugar solution. This is one where they were making rock candy. Have you ever made rock candy before or made any sort of a crystal? So on this, the solution was supersaturated. They heated up the water, they put in a ton of sugar, they carefully cooled it down, and then they introduced a seed crystal on a string. And over time, the excess solute that was in solution starts to come out and it starts to form these crystals. It's kind of fun to be able to do. So that's what we call super saturated. And that sweet tea that's really good that you want to drink, that is usually a super saturated solution. So what can influence your solubility? Well, solubility is usually influenced by two major things. The first is temperature. In general, as you increase the temperature, you increase the solubility of solids in water. So sugar has a huge increase in solubility. Now, other substances might not, like say sodium chloride salt. It'll increase a little bit, but not by very much. But sugar has this huge jump that happens. The other thing that can influence your solubility is intermolecular forces. So remember the old saying, likes dissolve likes. What this is referring to is that polar substances like to dissolve polar substances and nonpolar likes to dissolve nonpolar. And you're like, I think I remember those terms. We actually discussed some of these intermolecular forces. I believe it was back in chapter 6. And the idea is between individual molecules, there are some temporary attractions that occur. And the type of molecule that you have influences how strong or weak those interactions tend to be. A polar substance is a molecule that has what are called different electronegativities, meaning that the different elements, the different atoms, like the electrons more than some others do. So we get this separation of charges. So let me see if I can show you an example. So the example we show a lot in class is HCl. So HCl is a molecular compound. It's got a covalent bond in there. They're sharing electrons. So it's not like ionic. Ionic, they actually transfer electrons and there's a complete separation. Here, they're still sharing electrons, but it turns out that that chlorine likes the electrons a heck of a lot more than the hydrogen does. So to indicate that, we give it partial charges. So we can say that the chlorine is partially negative and that the hydrogen is partially positive. Now, because we have this separation of charges, this partial positive and partial negative side, when it comes in contact with another molecule that also has that separation of charges, the partial positive of one is really attracted to the partial negative of another molecule. Now, it's not a covalent bond. Again, it's only a temporary, short-lived, whatever you want to call it, attraction between the molecules. That is called dipole-dipole. If you need to, go back and look. So we had dipole-dipole, a special type called hydrogen bonding, and then between everything we have London forces, which are like instantaneous momentary dipoles. Now, if you have two things that are considered to be nonpolar, that means that there's no separation of charges. So examples of that is like if you get a diatomic chlorine. They're both chlorine. One of them doesn't want the electrons any more than the other. The other nonpolar substance that we talk about a lot is a carbon, organic compounds. So remember, this is going to have carbon and it's going to have a whole lot of hydrogens. Well, it turns out that carbon and hydrogen like the electrons about the same. There's no overall net pull one way or the other. So that's also considered to be nonpolar. So in our example here, HCl will not dissolve very good in, what is that, butane that I wrote on the bottom. HCl would dissolve much better in water than it would in butane. That's just because of this idea of likes dissolve likes. But the diatomic chlorine would like the butane better. I'm not saying it necessarily dissolves in there, but based on the chemical structure, that's what we would expect to see. So those are some things that influence your solubility. Now, on the next page, we have some pictures of this. All right, so here's a diagram that's going to show some of those different intermolecular attractions. Now, this one in particular is looking at Gatorade, and we've talked about Gatorade all semester. We've talked about the electrolytes in Gatorade. So Gatorade, the electrolyte portion is actually sodium chloride. But they add sugar because they want to make it taste a little bit better, because who wants to drink salty water? So let's look at some of the ideas dealing with solubility. Now at the top we have water. There's water. Now water is a polar molecule. It's a very strongly polar molecule. You have the oxygen that's partially negative and you have the hydrogens which are partially positive. So what'll happen when you put sodium chloride in water, because it's an ionic compound, it splits apart. So that's what's shown at the top. So here we have sodium ions, that's the positive charge, and that negatively charged chloride. Now if you would, take a minute and look to see how the water orients itself around that sodium and that chloride to see if there's a difference. Well, there definitely is a difference. Around that positively charged sodium, all the partial negative oxygens are right beside it. But if you look at the chloride, that water has flipped itself around and it's the partially positively charged hydrogens which are surrounding the negatively charged chloride. So this is one way that they'll stay separated, they'll stay suspended, and one way water is so interesting in that it can actually dissolve many of these ionic compounds. Now let's look at sucrose, at sugar. So here's sucrose right here. Now remember, the colors indicate what type of element it is. So we have all these little water molecules surrounding it, and the water molecules, the red is oxygen, the white is hydrogen. Well, on our sugar molecule, you can see that there's a bunch of carbons, and then there's some oxygens, and there's some hydrogens on there. Well, glucose itself is actually a fairly large molecule. So you're going to have a whole bunch of water molecules trying to surround it. And because it does have some OHs on it, that allows for a little bit of intermolecular forces called hydrogen bonds to occur to allow it to dissolve very easily. So let's see here. Oh, you can also see as you're looking at those water molecules that they have kind of turned and oriented themselves on either the oxygen or the hydrogen side to maximize that attraction, that temporary dipole-dipole hydrogen bond attraction with that glucose molecule. So that is a little bit about solutions and solubility and intermolecular forces.